Rankine cycle, the ideal cycle for vapor power cycles. The many of impracticalities associated with the Carnot cycle can be eliminated by superheating the steam in the boiler and condensing it completely the condenser. The cycle that result is the Rankine cycle, which is the ideal cycle for vapor power plants. The ideal Rankine cycle does not involve any irreversibilities. The process 1 and 2, isentropic compression in a pump. 2 and 3, constant pressure heat additions in a boiler. 3 and 4, isentropic expansion in a turbine. 4 and 1, constant pressure heat rejection in a condenser. Yes, on the images is a Rankine cycles of Rankine cycles. The first one is a pump, boiler, turbine, condensers. The energy analysis of ideal Rankine cycle shown in this figure. T vertical line is a temperatures, is entropies. Yes, the pump Q is equal to 0, boiler work done 0, turbine, condenser. The finally the efficiency is net work done divided by heat input equal to 1 minus heat output, heat input. These are the energy analysis. It's shown in the work done of pump in V equal to pressure P1 minus P2 and the ratios and enthalpy H1 H2 ratios mentioned here. The derivations of actual vapor power cycles from the idealized ones. The actual vapor cycle differ from the ideal Rankine cycle as a result of irreversibilities in the various components. Fluid frictions and heat losses to the surrounding are the two common sources of irreversibility. The isentropic efficiency work done efficiency P equal to W by Ws divided by Wa. The ideal cycles irreversibility in the pump in this lines they mention the pressure drop 1, 2, 3 and 4. 3 and 4 irreversibility in the turbine. The inside the actual cycles, the 1 and 2, the 4 is mentioned the pressure drop in the condensers. The first one is a derivation of actual vapor power cycle from the ideal Rankine cycle. The second B is equal to the effective pump and turbine irreversibilities on the Rankine cycles. The basics idea behind the modifications to increase the thermal efficiency of the power cycle is the same. The increase the average temperature at which heat is transferred to the working fluid in the boiler, or decrease the average temperature at which heat is rejected from the working fluid in the condenser. The lowering condenser pressures, low and average, to take the advantage of the increase the efficiency at low pressures. The condensers of a steam power plant usually operate well below the atmospheric pressures. There is a lower limit to this pressure depending on the temperatures of the cooling mediums. The side effect, the lowering the condenser pressure increases the moisture content of the steam at the final stage of the turbines. The effect of lower condensers pressures on the ideal Rankine cycle. Superheating the steam to high temperatures, increasing the high temperatures average. Both the net work and the heat input increases as a result of superheating the steam to a higher temperatures. The overall effect increases in the thermal efficiency since the average temperatures at which heat is added increases. The superheating to higher temperatures decreases the moisture content of the steam the turbine exits, which is desirable. The temperature is limited by the metallurgical considerations. Presently, the highest steam temperatures allowed the turbine is about 620 degrees Celsius. The effect of superheating the steam to higher temperature on the ideal Rankine cycle. The increases in the wet 3 dash 1, 2, 3, 4, 4 dash and 3. This 3 and 3 dash, 4 and 4 dash in between increases in wet net efficiency. Next one is increasing the boiler pressures. As on the two images, the effect of increasing the boil pressure on the ideal Rankine cycle, superheated Rankine cycles. For a fixed turbine temperature, the cycle shift to left and the moist content of the steam at the turbine increases. The effect can be corrected by reheating the steams. Increasing in wet W net, decreases wet net. Today, the many of modern steam power plant operate the supercritical pressures 22.06 megapascals and have a thermal efficiency about the 40% of for fossil fuel plant and 34% for the nuclear power plants. Next one is the ideal reheat Rankine cycles. Superheated steams to very high temperatures. It is a limited metallurgically. Expanded the steam turbine, two stages reheat in reheat it in between the reheats. These are the ideal Rankine cycles.